Good morning all. Today we are going to start with the second module of electrical machines design. In first module, we have studied about the principle of electrical machines design, types of enclosures and ventilation, heating and cooling in electrical machines, and magnetic circuit calculations. In second module, we are going to deal with the design of transformers. First, we'll give you an introduction about the single-phase transformer and three-phase transformer. You have already studied them in your electrical machines subject. We will begin with single-phase transformer. Its cross-sectional view is given here. This is actually the core type transformer. Its top view is shown here. The single-phase core type transformer consists of two iron legs, with each leg having one half of the primary winding and one half of the secondary winding. This low voltage winding and high voltage winding are provided in concentric form. Usually the low voltage winding is placed on the inner side, which is nearer to the core. This is done so as to reduce the value of insulation to be provided here. This diagram indicates the single phase shell type transformer. You have already studied the distinguishing features between core type transformer and shell type transformer in your machines subject in the previous semesters. In the case of core type transformer, the windings, both the low voltage winding and high voltage windings, are sandwiched between each other. That can be clearly seen here. This is low voltage winding, this is high voltage winding, then again high voltage, then low voltage, and this is the iron core. Based on the supply utility, the transformers are classified into single phase and three phase transformers. So far we have seen the classification of single phase transformer. Constructionally they are classified into two, that is core type transformer and shell type transformer. Next we are going to see the three phase transformer. Basically the generation, transmission and distribution of AC power and their utilization almost takes place in three phase. Hence, three-phase transformer plays a major role in the three-phase networks. This diagram indicates the three-phase core-type transformer and it indicates the three-phase shell-type transformer. Basically, in three-phase transformer, the primary and secondary windings are either connected in star or delta. A much clearer picture of the core-type construction and shell-type construction can be seen from here. This iron limb is surrounded by both the primary and secondary winding of phase A. The middle limb is surrounded by both the low voltage and high voltage winding of phase B, and this third limb is surrounded by both the primary and secondary winding of phase C. This is actually a three-phase, three-leg core type transformer. Similarly, shell type construction is also given here. This limb is surrounded by both the primary and secondary windings of phase A. This one is surrounded by both the primary and secondary windings of phase B, and this one is surrounded by low voltage and high voltage windings of coil C or phase C. If you see the magnetic circuit in the case of this core type construction, the flux will flow through the central limb and they will complete their path just like how this cursor is moving. See, if the flux which is going through the central limb is phi, then they will get split here. The flux which is going to the left side will be phi by 2 and the flux which will be going to the right side will be also phi by 2. Hence we can clearly say that the magnetic circuit is independent and series in nature. Next we are going to study about distribution and power transformers. This classification is made based on several factors like type of networks used, location of installation, and their usage either for low voltages or high voltages, etc. These distribution transformers are generally available for low voltage ratings. Low voltage ratings can be classified from 11 kV to 230 volts. They are usually having a power ratings which is less than 200 MVA. Generally, these transformers are used to step down the voltage to a standard service one. All those transformers which you are seeing besides the roadsides are actually these distribution transformers. They remain in operation for almost 24 hours a day. Since they are in continuous operation throughout the day, energy is always lost in this machine in the form of iron loss. Copper loss used to occur only when the machine is loaded, that is the transformer is loaded. Hence the amount of copper loss is having a dependency on the load cycle. Based on the consumption of the end users, the loading on the distribution transformers also changes. During daytime, it seems to be a light loaded condition for distribution transformers, while coming to the evening time, the load on the distribution transformer increases. Distribution transformers are always designed to have a good all-day efficiency value and good voltage regulation. Good voltage regulation means the voltage regulation value has to be a small one. Next we are going to see power transformers. These power transformers are generally used in generating stations and in transmission network of higher voltages. Higher voltages ratings are mainly from 33 kV to 400 kVs, and their power ratings is always greater than 200 MVA. These power transformers are always operated at full load condition. Therefore, these transformers are designed to have maximum efficiency at 100% of full load. Since the distribution transformers were not operating at full load condition, they were designed to have the maximum efficiency of operation at 50% of full load. In the case of a power transformer, both copper losses and iron losses occurs throughout the period of operation. Whereas in the case of the distribution transformers, just like what we said before, iron losses occurs throughout the day of operation, whereas copper loss occurs only during the period of loading. Generally, power transformers will be having the uses of both stepping up as well as stepping down of the voltage, whereas in the case of distribution transformers, mostly the usage seems to be stepping down of the voltage, as they are used as an end user connectivity. Now we are going to derive the output equation of the transformer. The various notations which are associated with the output equation and the design of transformers are given here. We will see to each one of them when and where it is required. Let's obtain the output equation. You have studied the relation for induced EMF in a transformer as 4.44 phi m Ft. In the case of induced EMF in primary, you have to replace the T term with N1, where N1 is the number of turns in the primary winding. If you want to find the induced EMF in the secondary, you have to replace this T with the term N2, where N2 is actually the number of turns in the secondary. EMF per turn can be indicated as ET. In order to obtain ET, you have to divide the induced EMF with the number of turns, that is E by T. Then you will be getting the relation as 4.44 phi m F. First we will determine the output equation of single phase transformer. Thereafter we will go to find the output equation of a three phase transformer. If you see the construction of the single phase transformer, that is single phase core type transformer here, this portion is said to be the window of the transformer. So in this diagram there is actually only one window, and you will be able to see each limb is surrounded by both low voltage winding as well as high voltage winding. Therefore, total copper area in the winding or in this window can be said to be the copper area of primary winding plus the copper area of secondary winding. If you see in this window, this inner winding is actually the low voltage winding or the primary winding. We cannot always say that the low voltage winding is the primary one. So I will say the inner winding is actually the low voltage winding itself. Here also if you see the inner winding is low voltage winding. So this window will consist of this low voltage windings as well as this high voltage windings. That is, it will have the areas of both the primary windings as well as secondary windings. Hence I can say the total copper area which is present in the window is the sum of copper area in primary winding and the copper area in secondary winding. That is written here. Copper area in primary winding can be calculated by multiplying the primary number of turns into area of primary conductor. In this diagram, inside the window portion, this portion and this portion indicates the low voltage winding, So this will be made up of numerous conductors. If you know the cross-sectional area of a single conductor, then multiplying it with the total number of turns, you will be able to calculate the area occupied by this portion of the low voltage winding and this portion of the low voltage winding. Similarly, in the case of secondary winding or the high voltage winding also, that is, copper area of primary winding can be determined by multiplying primary turns, that is, the number of turns in the primary winding, with the area of primary conductor, that is the cross-sectional area of the primary conductor. Similarly, the copper area of secondary windings relation also can be written as secondary turns into area of secondary winding. Number of turns of primary winding is indicated as Tp, and in the case of secondary winding it is represented as Ts. Similarly, As and Ap is also written here. As is actually the area of conductor of secondary winding and Ap is area of conductor of primary winding. AC is actually the area of copper in window. Please be clear with this term because we are going to find the area of copper in the window. So AC is equal to Tp is actually the primary turns and area of primary conductor, that is the cross-sectional area of primary conductor, Tp into Ap plus Ts into As. There is an actual practice. Tp into Ap gives the complete area of this portion and this portion, whereas Ts into As gives the complete area of this portion and this portion. Hope it's clear for you. In the next step, we are going to replace the Ap and As terms in terms of the current and current density. The current density term is indicated as del here. As we know, the current density in both the primary and secondary are the same. Therefore, Ap can be written as Ip by del. Similarly, As also can be written as Is by del. This relation is written from the standard relation of current density. That is, the standard relation of current density is current per unit area. Thereafter, making the substitution for Ap and As in AC, we will get the relation like this: Tp Ip by del plus Ts Is by del. That is Tp Ip plus Ts Is. You have studied this in a different notation in your DC machines, that is N1 I1. This might be represented there as N2 I2. And you have studied there the standard relation, that is E2 by E1 is equal to I1 by I2 is equal to N2 by N1. That is I1 by I2 is equal to N2 by N1. From that relation I can say that I1 into N1 is equal to I2 into N2. The same statement is represented here as Tp Ip and Ts Is. These two terms are one and the same. Therefore, they can be indicated as At. As we can see here, Tp Ip is equal to Ts Is is equal to At. That is ampere turns. Please keep in mind that the standard relation of transformer is E2 by E1 is equal to I1 by I2 is equal to N2 by N1. From that term, I1 by I2 is equal to N2 by N1, I can easily say that I1 into N1 is equal to I2 into N2. Here the notations used for I1 as Ip, N1 as Tp, I2 as Is and N2 as Ts. Since these two terms are one and the same, they can be replaced by a common term, that is At, that is ampere turns. Hence the relation for AC becomes 2 At by del. Next we are going to bring a new factor, that is the window space factor. It is actually defined as the ratio of copper area in a window to the actual area of the window. Actual area of the window means the total area of the window. This can be indicated as Kw is equal to AC by Aw. From this we can write the relation for AC as Aw into Kw, which is indicated as equation 3 here. Thereafter, for AC we are making the substitution we have obtained in the previous slide, that is AC is equal to 2 At by del is equal to Kw Aw. From this relation we will be writing another equation for At, that is At is equal to Kw Aw del by 2. You have studied in the machines class that the transformer is always rated in kVA. Now we are going to obtain the rating of the single phase transformer. The output power will be always represented in kVA in the case of a transformer, which is represented as Q here. So Q is equal to Vp Ip into 10 raised to minus 3. Vp is primary windings voltage, Ip is the primary windings current. We are multiplying it with 10 raised to minus 3 in order to obtain it as kVA. If we simply multiply Vp and Ip, then definitely the term will be only volt ampere. This Vp term is approximately equal to Ep, where Ep is actually the induced EMF in the primary side. Therefore, this relation can be also written as Ep Ip into 10 raised to minus 3. Ep is actually the induced EMF in the primary side. If we know the induced EMF per turn and the total number of turns in the primary side, we can easily calculate the value of induced EMF in the primary by multiplying the induced EMF per turn with the total number of turns in the primary winding. Therefore, we can replace the Ep term with Et into Tp, where Et is actually the induced EMF per turn and Tp is the total number of turns in the primary winding. In this relation, you can replace this Tp into Ip with At. In the last slide, we have obtained the relation for At. You have to make that substitution here. Then the relation gets modified into this form. Thereafter, you have to substitute for Et from equation number 1. Then dividing this 4.44 with 2, the relation gets into this form, that is 2.22 F phi m kW AW del into 10 raised to minus 3. Further replacing the main flux term with magnetic flux density and net iron area, you are quite familiar with the standard relation, that is B is equal to phi by A. From there we can write phi is equal to B by A. The same representation is made here also. Phi m is actually the main flux, Bm represents the maximum flux density, and Ai is actually the net iron area. So instead of phi m, you have to make the substitution Bm into Ai. Then you will be getting the final output relation of the transformer, of the single phase transformer, as 2.22 F Bm del kW AW AI into 10 raised to minus 3 kVA. All of you must by heart this relation, then only you will be able to handle the problems associated. Next, we are going to determine the output equation of a three-phase transformer. The procedure to derive the output equation remains the same as that of the single-phase transformer. If we look into the construction of the three-phase transformer, here you can see two windows. In each window, you will be able to see the primary and secondary windings of two phases. This portion comprises of primary and secondary windings of phase A, and this portion comprises of primary and secondary windings of phase B. Therefore, the relation for copper area in a window can be written as APTP plus ASTS into 2. This 2 has come here because each window consists of both the primary and secondary windings of two phases. In the single phase relation, this 2 were not there. This was because the window consists of only the primary and secondary windings of a single phase. So this 2 makes a significant difference in the procedures of obtaining the output equation of three-phase transformer comparing with that of the single-phase transformer. Thereafter, making the substitution of AP as IP by del and AS as IS by del, and TP into IP is equal to TS into IS is equal to AT. Making that substitution also, you will be able to get the relation for AC as 4AT by del. In this case of single phase transformer, we have obtained this relation as 2AT by del. Next, from the relation of the window space factor, we very well know that KW is equal to AC by AW. From there, I can write AC as KW into AW. So this relation is also AC and this relation is also AC. So we will be equating this two. Then we will be getting the relation like this. From there, I can write AT in terms of KW, AW and del. Next, while obtaining the output relation of the three-phase transformer, comparing with the single-phase transformer, here on 3 is coming because in the case of a three-phase system, the output power relation is 3 into V phase into I phase, or else root 3 into line voltage into line current. But for single phase it was just V phase into I phase, only Vp into Ip was existed there. So this 3 also makes a significant change in the procedure of obtaining the output equation of 3-phase transformer. So instead of this Vp you can substitute with the Ep because both these values are approximately same. Thereafter Ep term can be replaced by Et into Tp. Then in the next step we will be replacing Tp into Ip with At. Then we will give the substitution for At and Et. Et is actually the EMF per turn, so it can be substituted as 4.44 FIM, and At can be substituted as kW AW del by 4. Then while simplifying it, you will be able to divide this 4.44 with 4. Then you will be getting a 1.11 term here. After multiplying it with 3, it becomes 3.33 FIM kW AW del into 10 raised to minus 3. Further making the substitution for FIM as BM into AI, the final relation becomes like this. You must by heart this relation also. This relation is very much similar to that of the case of a single phase transformer, only difference is this term is replaced by 2.22. Hope it's clear for you. We have obtained the derivation for output equation of single phase transformer as well as for 3-phase transformer. Next we are going to obtain the expression for voltage per turn, that is induced EMF per turn, which we have expressed as E small t. We will first consider the output equation of a single phase transformer. We are quite familiar with this relation now. In this relation Vp is replaced by Ep, Ep is further replaced by Et into Tp, then the relation becomes 4.44 FIM TPIP into 10 raised to minus 3. TPIP can be replaced by At. For a particular type, service and method of construction of a transformer, the ratio of FIM to At remains a constant, which is generally represented as R. So from this relation, At can be represented as FIM by R. You have to make that substitution here. Then the relation becomes 4.44 FIM square F by R into 10 raised to minus 3. From here you will be able to obtain the relation for FIM. That is FIM is equal to square root of R into 10 raised to 3 divided by 4.44 F into square root of Q. As we know that the relation for induced EMF per turn or the voltage per turn is 4.44 FIM. Now in this relation, instead of FIM you have to make this substitution. Then further simplifying, you will be getting the final relation as square root of 4.44 F R 10 raised to 3 into square root of Q. In this term, F is actually the supply frequency, R is a constant, hence this whole term can be considered as a constant K. Therefore Et can be written as K into square root of Q, where K is square root of 4.44 into F into R into 10 raised to 3. Just like this term R had a dependency over the method of construction and working condition of transformer, this K also will have the same dependency as it is related with R. Next we are going to see a simple numerical problem. In this problem you are asked to find the core and window area. We used to represent it as AI and AW. Required for power rating of the transformer is given, that is Q's value is given. Single phase core type transformer. Assume a maximum flux density, BM's value is given, and del value is given, that is current density. ET, voltage per turn or EMF per turn, is given as 30 volt, and kW is given as 0.32. So we have to find the value of AI and AW. The value of AI can be determined from the relation for ET. ET is 4.44 F FIM. This FIM can be replaced with BM into AI. In this relation all the values are given except AI, so you can easily calculate the value of AI. Similarly, the value of AW can be found out from the standard output relation. All the parameters over here except AW is given, so you can easily find the value of AW also. With that, we are completing today's portion. The derivations we have studied are very important ones, and all of you must by heart the relations, then only you will be able to solve the numerical problems associated with it and the things which we are going to study in the upcoming video sessions. Thank you.